I think the mechanics Nova passed.
In electricity magnetism,
Yes, maybe there's one.
they passed.
Hopefully that was Zane.
Zen, yeah, he passed.
Was it Zane? Good.
Yeah,
Yeah.
they passed in
Yeah,
electricity magnetism.
He had to be passed this time.
Yeah, that is his last chance.
Yeah.
Do you know,
But I think he passed.
do you know if Zane passed thermo?
Yeah.
Who?
He has passed.
Yeah.
Good.
He
Good.
passed.
Yeah. He passed his qualified exam this time.
Yeah, he passed
Yeah.
thermal and
Yes. Electricity.
yeah, I can guess he is because
Yeah.
you put from number 1 to number 5, so you're first the new student. And the number 6 or 7 may be the old student. So I think he told me he will take a E&M and thermal.
Yeah.
So guess number 6 him.
Yeah.
That's
Yeah. He is passed.
Number one.
He has passed.
It's me.
And I think how many of us take on the exam of electricity magnetism? There were less people, less students.
Yeah. It was me, you.
Jane.
Zane.
Issue. I think only four of us take on the electricity magnetism, and I think only Jane passed the exam. He and I got the fail, and yours is pending.
Oh. That's fine.
Okay, after finishing our
I'm
mathematical
curious
exam.
about your result.
Yeah, I
Don't
think
be. I'm not curious.
Okay. If you have same the subject, you have to take again. If the subject match,
You have
we
3
can
checks,
study
right?
together.
yeah.
Okay.
We can study together. For
Few times we
upcoming
have
days.
for us, so we pass
Don't worry.
Yes.
easily.
Yeah.
2 times to
You're
yeah.
trying to survive this.
We
Yeah,
have.
yeah. Me too. Mathematical. Oh,
Yeah.
today's test. I forgot that.
Okay, I should.
You're just gonna stress yourself out. When you study.
I'm on chill.
I got the result exactly what I predicted earlier.
Yeah.
Yeah.
He always used to mention that I think I will gonna fail in classical mechanics and I think I will pass quantum mechanics and thermal physics, and he, as he said, he mentioned and he actually gave the same result.
Wow.
In my case, I thought I will pass the electricity and magnetism. I think that was the best exam for me, but I won't get the star.
How many exams is this mathematical physics or physics? Mathematical physics.
Mathematical physics second test.
You have a total 3?
Three
Three
tests,
tests.
yeah.
Three
Okay.
total.
We have already taken one, and today is second.
Second.
And we have December 1st. On December 1st.
Okay,
What is-
December 1st.
I think.
So before the December 1st is the last class, right?
Yeah.
Okay. That's good. Then our exam
Mm-hmm.
Yeah.
after that.
After
Yeah,
that.
yeah.
So you have time.
I think at the end of January.
Yeah.
In or beginning? No, beginning. I think end of January we will have qualifier exam for spring. Class will be start at the mid of the January.
Around when would be the classical and quantum in class, Dr.
Sorry?
Classical?
Let me remember. I think
December.
after December.
Is it the 8th and the 15th?
Yeah, I remember something 8th or 9th.
In person or
This 9th
in class? In class is that?
syllabus.
I can't remember if it was for classical on the 8th or.
Yeah, 8th in class. And December 1st, last day, I will give you this take a home. So this 50% take a home,
Yeah.
50% in class.
In class portion will cover from homework questions or all the exercise questions.
That's from the after the break we cover, right? Chapter 3 until I hope we can finish at least covered the first few sections of chapter 10. So today we finish
After chapter 3
chapter 3,
and the remaining all.
chapter 8,
Yeah.
9, and part of chapter 10.
Yeah.
How will the in-class proportion work? Is it just like an hour?
It is as before. 3 or 4 hours. It's up to some students, maybe 1 or 2 hours finish,
Yeah.
but some others it takes time. So
How
that's
many
what-
questions?
usually 3.
3 questions.
Small, not like take a home is big, right?
Yeah.
3 questions, 3 hours?
She has some example experience as a quantity. So I just
Okay.
okay. That is this. Oh, this is. Okay, so that is if December 8th, if you're all available, then we can. How about you? Yeah, just think about you have other class, right?
Oh, no, I already, this is my only class.
Oh, okay, that's good. So yeah, then that the quantum after that we 11 or something. I remember because quantum we have the last class is December 5th or December. I forgot. Yeah.
If I write 3 hours,
Just brief review what we discussed last time, then we can continue, finish the schedule today. Description is eccentricity. Yes.
These 2. And the others. Art.
Okay. And in this case, we will this minimum. This is a so that is this one is 5. Then we have this the O10. The O10 is go to infinite. So we have from the orbital we have this one equal to 1. So from here, then we can calculate the skirting angle to try to do this. And from and this one, given we have the result is cotangent half theta equal to the constant 2 ds. Z is 1 equals e squared. So that gives us the we have the s as a function of then we got this cross section, differential cross section. Okay. ds d. I didn't give this formula here. S over sine theta and d s theta. Right. So then we have when you calculate this, that is the prime is square over 4 over sine square half theta. Then we have the differential cross section. This is which we discussed. The total cross section go to infinite because it's a Coulomb force. Since when this scattering angle equal to 0, this one go to infinite, so that is what happened. It's table like this. So sigma is the differential cross section of function of theta is like this. So here let's convert. Then we take the integral total that gives us infinite. That is we discussed. Then we go to case 2. We also discuss case 2. Okay, here I have here this one, the S and the angle is 1, 2, 1 correspond each other. 1S, we have a 1 scattering angle. But when we discuss S and S is or are not 1, 2, 1. In that case, example here we have example if this potential is like this, this positive potential, the energy is higher than this. So what we found is the scattering S as a function, the scattering angle as a function S is like here we have a maximum. If this is pi smaller than pi, and for any scattering angle we have not only one S, we have 2S, S1, S2. So because this okay. Because this, then this differential cross section, this formula is 1 by 1 case. But if we have one scattering angle with 2S, so we have sum over all the possible at I, all the possible S, which for given theta, we are getting scattering, so that is SI sine theta is the same, right? So only the S change. DSI is the same. That is in general. Here, all possible. Yes. And for this case, you will see since we have this maximum here, then this derivative, if they take this derivative equal to 0, right? So then, or you take inverse is 0, then go to infinite. So that you go to infinite, then theta go to theta maximum. That is here like this. But after above angle above this theta max, there's no scattering. That is one case we discussed. Now we are going to discuss, or continue to discuss today case 3. So if the scattering is a combination of attractive and repulsive. How about this case? So now today, this case is complicated but very interesting. So let's give some of a brief discussion about this. Think about if the force is attractive, what kind of scattering? Okay, let's consider if this for repulsive. For repulsive force, what kind of scattering? Like this, right? The orbital is always from here go like this. It's like towards to the out of this center, right? So over this one, the orbital is over this the particles. The repel particle. Just simple. Repel. This will repel particles outward, right? Deflection outward. Like this. This is outward, right? So that is like this. Okay, the particle come here. If this is repulsive, which I correct as well. And we have it is the same. But how about the attractive? Attractive force. We'll try to attract particle, because this is the center, right? Attract particle like this, right? This is remember we discussed before this gathering, we all discussed attractive negative force, and this trajectory is still hyperbola, but this the center force is inside, right? So that is attract or pull the particle in towards the center, right? Here, towards the center. So that is case. So that is a pure repulsive, pure attractive. Then if this force is combination of these two, what will happen? That's which one dominate, right? So we are going to see. Okay. Let me first discuss some of the concept, and then we are going to discuss it. So now let's consider the following cases. So for example, if the first one, if I have an incident particle here, V naught, go to this way, and then come to the center here and then go back. So this is R minimum. Just, there's no rotation, just come to here and come back. So what is the angle of this? Oh, okay, this one is we define here, right? The angle between the incident over the R naught and with R minimum. How much? It's 0, right? If you consider like this. So this is the angle, right? Between the initial R naught from center to the infinite to the R minimum, or if you consider from the R minimum, between the R minimum and go to the infinite, this is an asymptotic line. So that is the angle of this definition, right? Now in this case, we have the line between these two is 0, right? So the line, if either go to infinite or come in. So either R naught is this way, and R naught, if you consider initially when here, so that is R naught, right? From here to the position, initial position, and between R naught and R minimum is 0, right? So that's 0, and in this case, this is a pi minus 2 side, right? So that is pi. And that also makes sense. What is the definition of this? This definition is the angle between incident and deflect, right? This one. So incident and deflect just opposite. So that is pi, right? Okay, so that is the case. Second one, if we have this one, so minimum, and we know this angle is less than half pi, right? And in this case, we know the theta, the scattering angle is multiplied this one is it's less than half pi, so this is less than pi. Actually, also less than half pi. This is less than half pi. Pi is less than pi, so less than. Let's see this. That is of course is less than pi, right? Then say 3 cases. Suppose we have this go further. So that is the center of this force. So R minimum is here. This is phi, right? Sorry, flat like psi. And in this case, psi equal to half pi. Then the angle scattering angle go further. So that means the same direction with the incident direction, right? 0. Right, that makes sense since this is scattering. Okay, how about this case? Now we are going to consider a little bit complicated case. Now is this one, right? So now I'm going to do this. So this is center here. This is minimum. And then this is the angle, right? It's kind of attractive. So this case is larger than half pi, right? Still less than pi. Then this is pi minus 2 psi is negative. I mean, negative means just, you see here, if you consider this direction, and this direction, that is theta, right? If you select the counterclockwise is positive and the clockwise is negative. That makes sense, right? Now, number 5. Suppose we have this, the particle, just erase this part, space. The particle, suppose this is center, right? The particle come to here and try to traverse to the center, and with some of rotation. This is center here, and make it even smaller, and maybe bigger and back. How about this case? Several cycles, right? So in this case, it's definitely larger than pi, and then this angle is you can say, let me still write down here, less than, but maybe also include some 2 pi circles, right? So that means we have the particle come to close here and try to make the rotation about the center, and of course the radius also change, go to the minimum and go increase and then go back. So this one, when I say here, I have not say detail, just larger than that, but how much it is depends on how many circles here. But this case is also here, actually is many circles here, but I didn't write down here. But we want to discuss examples, then we can go to some of the features. Okay, now let's consider the potential. Then we are going to discuss potential with initial energy. Then let's see what this looks like. Depend on the initial energy, right? So example, if V prime is, remember V prime is this factorial potential plus V, right, the real potential. But now the real potential has 2 terms, attractive and repulsive. So I'm going to separate it. Attractive plus repulsive. Okay, that is the case. Now, that is potential, so now let's plot potential as function R, V prime. Let's consider for L equal to 0 case, right? If L equal to 0, only these 2 terms, right? So one is attractive negative, another positive is repulsive. Add together, so I'm going to just plot this V prime, not each individual. So that is something like this, right? If the repulsive dominant in the small r and attractive in the large R, so something like this. That is for correspond to L equal to 0. So L equal to 0, remember S is L square root of this formula. So in this case, this line S also equal to 0, right? So you can see what is S equal to 0. This one is 0. So that is which one? Something like this, right? That is this case. Okay. So that is, if I plot, okay, let's plot together. So now let's consider the next one. Next one, L is not equal to 0, so we have this term together. This is a positive, repulsive, right? The two repulsive and plus attractive, so the combination is something like this. Example is here dominates the attract, but then when R go to increase because that term dominates, so we have something like this. There's a bump here, above. Okay. Sorry, let's see this R1. This R0 is not important in our case. It's not important, but so that is one case. That is, I'm going to say L1, not 0. So, but this curve is correspond to L1. And another one, I think another one is this attractive and the positive try to balance, make this bump become lighter. And here, I'm going to say this lighten here is R2. So this is L2. This term determine the L, right? Then the number, the last one, I think the last one, when L increase, the repulsive term increase, so dominate, right? Okay, now we are going to discuss different cases, depending on the initial energy, which kind of scheduling, right? So now let's discuss first case. Start from the beginning. So now, this question. First, L equal to 0, so S equal to 0 case is this curve. So for this curve, since we're interested in scheduling, right, we just consider energy positive. Energy negative, we know this boundary, form this closed orbit like ellipse or something, right? So that is, we already discussed. So, just consider this case. All right. Okay. And then let's first the I think that is not this is so at minimum case is 0, right? Oh, okay, sorry. When I say minimum, let me, I don't want to make this too tricky. Here, this is the energy positive, right? So here is across this minimum. This is a but consider this is just this curve, not others, right? So in this case, we have a minimum here. Then we know there's only one turning point here, right? Minimum. I mean, this case, how about this one? We have angular velocity. Angular velocity equal to L mr squared, right? Because L equal to 0. So this kind of scheduling is like this, right? So the scheduling is like incident, come to here, and then come to here, which is this is our minimum, and go back, right? So that is only this case. And then we know in this case, this angle is 0, and if you remember the formula, this is the integral. Just use this one. So that is pi minus 2 psi. Pi minus 2 and psi is the integral from R minimum to infinite, since R now is infinite, and this one as if I use R, okay, fine. That's R squared 1 minus 3 over E minus square here. This one is b pi minus 0 equal to pi, right? This is exact this case. Okay. So this case is simple. Since the angular momentum is 0, we can only have this type of scattering. Now we discuss the second case. Second case, L equal to L1. Okay. L equal to L1, and let me get, in any case, S is L1, formula here, right? L1, 2m. So depend on this one. The S, the textbook, that figure is something I think they misleading. They say this is a S0, S1, but the whole curve depend on initial energy, so that the whole curve is not S1, only L1. So here, S will change depending on initial energy, but L1 is fixed, right? So that is the information here. Okay, now let's discuss the, for if the initial energy is just equal to E1, so which is E1? Just equal to this maximum here at the bumper. Okay, if that's the case, then at this position, S, we can define, this is S1, we define, that is when energy equal to E1. So at this point, or when the initial energy is here, then the particle move in this, along this curve is always with S1. That makes sense? If energy is either lower than this, higher than this, S is not S1. But when, so now we consider this is, in this case, S1. Then what happened? So you can see the particle from infinite far and come to here, and what happened here? So at R1 dot is 0, right? Because this energy equal to this maximum V prime. So that we already discussed before, right? That is 0. But theta dot, here I'm going to say theta 1 is, say theta at this position. That is L1 2 MR1. That's not 2, MR. And then in this case, since L1 equal to this, you have M R1 square, and L1 is S1. Or you observe M inside this become denominator. So whatever we have the non-zero, right? So what happened? The particle, okay, suppose this is suppose this is center here, right? So now we see the particle come to here, try to with just equal to R1 here, and make the circle, because really will not change. Always keep here, right? Infinite rotate. Rotation at R1. Then what is angle here? So this integral is just integral. And you have the result, because that integral is like this. But this one is R chain. So that is something like the here now. I'm going to say that. Oh, okay, now, right now, I'm going to introduce this. When we have more rotations, so the actual calculated angle with the formula, with this formula, will more than 2 pi, right? But whatever, when suppose in one case it is scattered, then what we measure? What we measure scattering is the angle between the incident and this one. So that's be, this is theta, right? between this line and this line. That is measured. Measured scattering angle. So this one is calculated. This one is calculated angle. Therefore, we're going to distinguish these two, so we introduce another capital phi, which is a calculated angle, scattering angle. So that is defined pi minus 2 percent psi is the integral from minimum and to infinite, and really depend on what kind of details, maybe rotate with certain circles or just no rotation. It really depends on energy and what kind of curve, right? So that is. Then we're going to say, okay, this one is equal to what we calculate this real, but subtract all the rotations. So we define the measured or observed scattering is equal to plus minus here what we calculate and minus 2 m pi. M is an integer number. Okay, so that one, if this is a calculated and also this is observed or measured. Observed scattering angle. That is in case if we have this type of sense pattern, then we are going to subtract how many terms. Calculate this and subtract those, and then give us the final measure or observed angles. Okay, so that is a case when energy just is exactly equal to E1. Then now let's consider 3K still L equal to L1. So S still equal to L1 to ME, but now energy is larger than E1. Now let's still consider this curve, but now if the energy is different color. Now this is big, so I just, so that is energy here. Okay. Suppose in this case, then the initial the angular momentum is still L1. So when the particle come from infinity come to here, what happened? At this position, because energy difference small, so this R dot is small, right? Slow, but still not zero. And then we have that means particle come too close to this position, it will slow down, but still keep the rotation. But since the R dot still not zero, that means the R still change, right? So it will change, it will keep continue. Continue until to here, right? If this is the R minimum in this case, then go back. So what kind of scattering? Okay, in this case, S, I'm going to say L1, so we do not know how much energy, but it is, because this is larger than E1, so this is smaller than S1, right? We just know that. Then the case is like, okay, I come here, the particle from infinity come to here, and then at R1, and then because R1, okay, R1 dot is not equal to 0, right? Zero dot is also not equal to 0. So keep continue, rotation that keep reduce the R until go to, suppose this is a, now this BZ here, but if this is R minimum here, R minimum, come to here, right? And this position, the radius will not change, keep the same, because it's R dot at that position. R dot minimum is 0, right? But the 6 dot minimum is non-zero. So we keep continual rotation and here, and finally come to here, right? So we have several terms, but this term, not like this, keep same radius, it will change. Decrease, decrease, and then increase, 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 right? Go back. But the formula similar since we have the integral here, this one, the larger than is this case, right? That is, I didn't write down here in details, but now we have introduced the calculated angle, scattering angle, and observed scattering angle, so we have the idea about this. So, in this case, the calculate one to be pi minus 2 from this R minimum to infinite as the R square 1 minus A over E minus S square. That's be pi minus 2 m pi, right? Depending on how many circles. Something like here, I did I? Yeah. Pi minus. Oh, okay, not this one. This one is 2. Okay, 2. Yeah, this is pi minus sum of value and how many terms you do not know, right? So that is something like this. But the two type of rotation. One is a change R at the radial, another keep radial. So this is the case. We have repulsive and then come here, the attractive dominate. So make this towards the center rotation, and then go back, and then keep going to the far away. So then it become a repulsive, right? Dominate. So that is this case. Okay. Now, I leave this energy smaller than E1. You are going to think about yourself. Just follow the same thing, but you can think about yourself, what will happen. Okay, now I just leave another case, just discuss one case that we for you to think about. Since we have a lot of issues we can discuss depending on the initial energy, right? Number 4, now we consider L equal to L2. So now we are going to consider this curve. With this curve, S is L2 over square root 2 and E on, okay, depending on initial energy, right? So now let's consider if energy is just equal to E2. So now which one is E2? I'm going to say this to E2. Just at this position R2. So at E2 we have S2 is equal to L2. For this energy, then what will happen? So the particle come from an infinite position and close to the center of this is center, right? Then at this position R2, the radial and R2, right? So the R2 dot is 0. Of course, theta 2 dot is not 0, right? That how much you can use the formula, right? That's dot. L2 and R2 square, right? And L2 you can use the greater S2. Then you know that is non-zero. So what happened is what kind of the scattering here? We cannot go in, right? Because it's energy forbidden. So we'll go back. So that means the particle try to like this, right? This is repulsive, kind of repulsive, right? In this case, it's R2 equal to R min. So in this case, this one is smaller than this case. And this is like, in general, like this Rutherford the scattering, the pure repulsive. So I just, so here is equal to, I think in this case there's no circle, so they are equal. The calculate and the measures equal 2 pi minus 2 psi, and the psi is the integral. I just save time. So how to obtain this one is the integral, right? Calculate. Yeah. In this case they are equal. Okay, and then the remaining part you can discuss. I also give you either energy is larger than E2. What happened? or L equal to L3, what kind of scattering? Okay, now I'm going to give you a little bit summarize what kind of scattering. So as a S, I mean the textbook here also misleading some. So it is not the S increase from 0 to infinity. It just gives S as here, and with different S here, this is a calculated pi angle. So suppose here we consider S1 is this one. Is this case, right? I mean, if energy equal to E1 is this case, otherwise not. So what happens? If energy equal to E1, the angle here is infinite, right? So you will go down because the pi minus integral is negative how many? So that is like singularity. So that is energy equal to E1 case. Then if energy is smaller than E1, you know the S here is smaller than S is larger than S1, right? So this here is S larger than S1, but sum of it is S smaller. So I just consider in this range, and you will see the angle will increase. I mean, rotation becomes smaller. So that is this is smaller. If smaller, you consider is like this here, right? This is smaller. Come to here, back, right? So that is what happened here. Then if energy is larger than E1, then this S is small. So this is, and depend on the energy, how much. So this is correspond to L1 case. Energy, if energy is much higher, this will not affect. So then if energy is much higher, even though we have a bumper here, but it will go, right? In that case, it's pi, right? So that is the limit here. And then another case, S2 and S3 case. So in S2 and S3, you will see that whatever the case is always like repulsive. So repulsive, most general case is like this, not S and angle is not one by one response, maybe like here, and just click it. So that means for given angle, here we have a let's see, like S3 here. Okay, yeah, they are not, so now I'm fine. So this is angle, and we have 2S value here, right? That is a summation for all these possible S for giving the same scattering angle. So this is the textbook give this figure, but you just do not think about this as X from 0 increase. Just ignore that, but just consider if we have this case, what kind of angle behavior we can this case, what kind of behavior. Okay, so we finished the scattering, and actually the chapter 3. So now, we will go back to our chapter 2. We focus on this Lagrange equation, actually equation motion, how to obtain or describe any particle with what kind of motion, right? So now we come back to see the theory again, and then we are going to develop the theory from Lagrangian to Hamiltonian. Okay, so now we are going to go to chapter 8. The issues here, let's remind what we review chapter 1 and 2, right? What we discover, we introduce Lagrangian. And the Lagrangian is basically it's just the difference of the kinetic energy and potential energy, right? And here, since, okay, first, that is contain all physical information, right? That means when we introduce of the system, when we introduce the Lagrangian, this include all the information, so we are going to see the dynamics of Lagrangian that will give us the dynamics of the system. So here, if you remember, we introduced generalized coordinates, generalized velocity and time, right? So that is means the Lagrange is a function of this. I will not write down detail, you know this QG, right? This generalized, maybe angles, maybe displacement, maybe some others. So, with this, and then if, okay, if the system satisfies the two conditions, like chapter 2, we consider monogenic. Do you remember what is monogenic condition? Who remember? The force is always gradient of given the scalar field, right? This is the scalar field. If it exists a scalar field, then if the system, all the force can be written in this way, then we call this as monogenic. And then, monomic, what is condition? The constraint, right? Type of constraint, we use F alpha, which is only function of Qg and time, not Qg dot, right? Equal to 0. So if these two conditions satisfy the system, then the equation motion, okay, the equations of motion of system follow Lagrange equation, right? Lagrange's equation. That is total time derivative of partial L, partial Qg dot, partial L, partial Qg equal to 0. G from 1 to n. N is what? Number of independent general coordinates, right? Number of independent. Of course, in chapter 2, we also discussed, extended this Hamilton's principle to the case if we select the group of the general coordinates, they are not independent, it still can use it, but here then we have this QG, that may be this holonomic force, maybe this semi-holonomic. Remember, we have that detailed discussion, but I do not want to remind you that because we are going to study from here. Only this condition will transfer to the Hamiltonian. Okay, so the other, if we are interested in the force due to the constraint, we can introduce a group of non-dependent, independent general coordinates. We can set up an equation that then we can calculate the general force which associates the constraint. So now we will start from here. If the system satisfies these two, then we can definitely, because if we satisfy these two, we can definitely select independent general coordinates, right? Remember the condition. Then equation here. Now, from this equation, the question here is the second order differential equation, right? Partial differential or whatever the differential equations. How many? We have n, right? Since J from 1 to n. So what we are going to say, in principle, yes, we can solve, since we have this equation. What we need to write down, we have several homework or exam. Right? Find the kinetic energy, find the potential energy, find this suitable general coordinates. We are going to write this in terms of this. Then we are going to do this. So we set the equation, then we are going to solve the equation, find the Qg as Qg time, right? And then from here, and then go back to use the transformation equation, find R as an R, right? That is the schedule or procedure we use. But the key is here. This is difficult. Since this differential equation, first is second order, and not the simple second order differential equation. It's very complicated. And then for each one, they are not independent. We have n equations below, you remember, right, before. Self-equation have cross term. So that is difficult. Yeah. Difficult to solve. Then people, this is we just consider in general. Some of the case may be simple, but most cases difficult. So we are going to develop the theory more general, try to make this procedure easier. So now our goal, what is our goal? Try to reduce the second order differential equations to first order. Right? If first order, any first order differential equation, we can do the integral. It's in general we can do. Second order only for some special case we can do, right? So if that is the case, then that makes our to solve this problem become easier. Then how to realize this goal? Now the question is how to realize. Okay, we have sent the physicists consider. We just follow what we consider. Remember, we introduced the conjugate momentum, Pj. Pj equal to what? Partial L, partial Qj dot, right? Okay. How many G actually from 1 to, we have n conjugate momentum here. So if we select this general coordinates as independent, and then we take this conjugate momentum also as independent variables to form the basis of space. Let me just say space, and then we are going to get the name of this space. Then any function can be function of Qj, Pj, or if we consider time. Right? We can write any function in terms of these two variables, two set of variables. So in the Lagrangian, that is the idea. And then if we can introduce, if this one, if this leads to the first order differential equations of motion, then that is our goal, right? So you see here, we want to reduce. And how to reduce it? We consider another space. In another space, this space is built by the general coordinates and the conjugate momentum. Then this space, any function in this space, if this function in this space can derive this equation motion from second order to the first order, so that is our goal. Then, now, how to do that? So now let's compare this, let's try to compare this real Lagrangian is function of general coordinate, general velocity of t, right? And then now, okay, let me see here, I gave the name. I'm going to introduce Hamiltonian. So now we have a Hamiltonian, which is in this another new space, which is general coordinate, conjugate momentum, and time. So this one is here is in this, we already introduced configuration space, right? Configuration space. So this L is defined in configuration space, Q1, Q2, Q3, and any point here is a state of system, right? At the beginning I introduced this. So any point here that is for giving general coordinates, we can define this point here. And from this point to another point here, from A to B is the dynamics, right? So that is a system take the path. So that is described as Lagrangian. That means Lagrange is defined in the Hamiltonian space. Then we follow the Lagrange equation here to solve this dynamics. Now, in this case, we are going to say give a name of this new space. We call it phase space. Okay, phase space here. This space is the base. Base set is just general coordinates. They are independent. Here, this space 2 set. So that is 2n. This is n. Dimension n, right? This dimension is 2n. Then here, what happened here in this case? I can only plot the 3D. I cannot plot n more. So suppose this is Q1, Q2, and this may be Q1. So any state here point is also give a state, this current state of system, dynamic state system, and also when from A to B, we have this dynamics, right? Same things, but we use different space. So now we are going to see transformation. Space. Okay, so you see this is our goal. And now let's just introduce the Hamiltonian in this phase space. And we are going to set up the relation between Hamiltonian and Lagrangian, or in other words, we already have the story for Lagrangian in the Hamiltonian space. We are going to transfer this story to the phase space. Then we are going to find out how to transfer Lagrangian to the Hamiltonian. If yes, then this equation can automatically transfer to that, right? That is our goal. Okay, with this goal now, the first question is how to transform, right? So now let's just discuss now the technique or procedure how to transform. And this one is actually it's not difficult but easy. So how to answer it, we are going to use the Legendre transformation. Mathematically, there's a very easy way to transform. Transformation. Okay. This transformation, you can see the interesting here. Look these two space. This space is Q, right? This space is Q and PJ, QJ and PJ. Here, the Lagrangian is function of QJ, and the Hamiltonian also function QJ. But Lagrangian is a function QJ and QJ dot, right? Two variables. But here, this one different. So what does it mean? This two function has a half of is the same variables. The others not. So if we can transform the QJ dot by PJ, then we can get this transformation, right? So that is go. And how to do that? That is this Legendre transformation. Legendre transformation, what does it mean? So, okay. So if we have a function f is a function of xy, right? Then now we are going to transform the f to g, which is a function of, I'm going to keep y, but x, I'm going to use another one, u. How to do that? This is not arbitrary, no any connection, but there's connection. You will see u, what is u, right? So now first, let's consider this step. If f is a function xy, and then df, total differential is partial f, partial x, for y, keep constant, and dx plus partial f, partial y, x dy, right? Then we are going to define this one as a u. So that is u here. So u is the first order difference, partial differential of this initial function f with respect to the variable, first variable x, dx, and here is v dy. So v, let me just partial f, partial x with y is u, v is partial f, partial y x. Okay, so that is this part. Then now let's consider this one. So if we introduce g as a function, is a function of uy such that, how to do that? If we define the g as this one, f x, which is variable x and y, minus the product of ux. If I do this way, I can automatically transform, you see the half is x transfer to u, right? But I still keep y. That is just transfer half of the variable. So now if I define this, let's see if it is automatically transferred. Let's look at dg. Okay. Dt by definition should be df minus u dx minus x du, right? Okay. Then df, I already write down here, is u dx plus v dy, then I minus u dx minus x du. So this one is going to cancel. Then I have v dy minus x du. So that means that is these two variables, right? That immediately gives us g is a function of u and y. And here, v is partial f, partial y for fixed x, but also partial g, partial y for fixed u, right? Then x, in this case, is partial g, partial u for fixed y. The relation here. So, very simple, right? And this is not unique, right? We can also do this alternately. We can also define g is equal to just change the sign, minus f plus xu. Then you can see dt is df minus df plus x du plus u dx. Then minus df is minus u dx minus v dy plus x du plus u dx. Again, this term cancel. So we have x du minus v dy. Yes, we can also transfer the g from f is a function of u and y, right? So here, you see, I just change the sign. It's the same thing. Okay, I mean, same thing is we can transfer the formula, but this one and that one may not be the same, right? So that just we can reach the goal is transfer from here to here. Okay, so with this, now we are going to see how to define h such that we can transfer L to H from the convolution space to the phase space. So we are going to select which one we are going to change, right? We keep this one. So this is like y. We keep y is qj, but the qj dot is x, right? So we are going to follow this. So now the L, then we rewrite again, is qj dot and t. So here, this is like y, this is like x. Just compare here. And Hamiltonian is equal to qj, pj, and t. So here, this is again, this is y. We keep y, do not change. We just keep t. So here, just be u, right? And is this u? Let's see if this b is, right? So now let's do. So now we are going to, so that means if we want to change, we are going to define h is, I'm going to use this one. Not that one. So minus L plus x is qj dot, right? U is Pj. But here we have summation. This is only two variables, but if there's more, then you can just sum. So you agree with this is the definition. So now let's see if yes, it can transform L to H. Let's see that. So dH is minus dL plus J Qj dot dPj plus Qj dot and Pj dQj dot, right? Okay, dL. So dL is minus, let's say L. L is function of Qj, right? So that is Q partial L, right? So that's partial L, partial Qj, dQj, sorry. dQj, that is this term and plus summation partial L, partial Qj dot, dQj dot, and partial L, partial T, dt, right? That is this part, this dL. And then I plus, you come? Okay. I still have a few minutes, okay. I think I finished this one and you can prepare for the exam. All right, so now here, that one, right? So, J dot, dQ, and dPj. dPj plus dPj dot. Now this one, if I keep continuing minus, remember this one? Lagrange equation. Minus, so that's equal to, right? Minus is equal to 0, so I move this term to the right hand side. So that one is, this one is, do you agree? This is Pj, right? This is Pj dot, because two times. So here, minus first is Pj dot dQj. Second one, this one is Pj, right? Because this one is Pj. dQj dot plus partial L, partial T, dP. And the remaining part we just should Qj dot Pj plus Pj dQj dot. And here, this term, right, this is negative. This is negative, and this positive, right, they cancel. And Qj dot dP, okay, that keeps that one. So now, that is equal. Okay. I move now, since this term disappeared, and I think I have a one Qj dot, this one keep here, and the Pj dot, this one, yeah, this one cancelled, right? This one cancelled. So we have only three terms. Okay, three terms. Now I put this positive at the front. Qj dot dPj minus, the first term is Pj dot dQj and minus partial L partial T. Oh, yeah, partial T. dP. So you can see here, this is a variable. That is this. Right? So that means, yes, we have that, yes, if we define that L is this one, we can come or transform from, H is this formula, we can transform L from the convection space to the H to the phase space. So yes, now we have this in general, so now usually we just put the positive term in front. That is Hamiltonian. Okay. So now when we do this, then that is a function of the automatic transform Lagrange to Hamiltonian. So now, if this function of Qj and Pj, so dH is b partial h partial Qj d Qj plus partial h partial Pj d Pj partial h partial t, right? And that this supposed to be equal. So you can see here, this is a Pj here. Let's do this. Yeah, dQj. Let's consider this one. So first we have equation. Maybe consider this one first. dPj, right? So now here Qj dot is equal to partial h partial Pj, right? Then Pj dot is equal to negative. There's a negative sign. This one, right? This two should be equal to negative partial h partial Qj. And then the partial h partial t is negative partial L partial t. Here from 1 to n. This is the equation motion for Qj. This is equation motion for another. So you see this reduced to first order, right? These are first order. So yes, we do the first order. How many order differential equation? Equations. How many? 2n. Since we have this one, each j value we have two equations. We reached our goal. Okay, so now today I just stop here. And we can start from here next on Thursday. We are going to discuss how to do the details. We know how to transform, and they give us some procedure how to do that, and introduce matrix representation, which can easily help us to remember the relation between these the different terms. Then we go to concept symmetry and conservation, and some examples. You have a question? Okay. All right. Okay. Just remind you the homework due on Thursday. Okay, good.
There is no
Here. Here.
there is no food in vending machine. So how many style
That's the one that I written.
You guys have sent in one item and
yeah. So you will start from mechanics, classical mechanics.
Yeah.
And in format,
Let me double check you. You are number 1?
one.
I'm one.
You one.
Yeah, mine 3.
3 and 1.
5.
5. Okay. 1, 3, 5. Yes. Check it.
You have checked StatMech paper. You are the grader of.
I just graded a few thermal.
So
Thermal intermediate.
intermediate.
Yeah, and the mechanics intermediate.
Mechanics intermediate.
Yeah.
Also you have checked.
I have only graded these two. And other faculty grade some other part.
Not quantum.
No content. Content maybe Dr. Smadish or some other.
And electrodynamics.
No, I think that's be Dr. Chris David and maybe I do not know who, but he teach that class, right? Usually who teaches the class? I just teach the content since last semester, last year. Before that, Swedish, Dr. Swedish. So I think that he take care of that. Okay.
Thank you.
Good luck of this final this exam you are going to take.
Thank you.
क्लासिकल र स्ट्याटमेटको
क्लासिकलमा फेल गरिरहेको छ नि त
हो रहेछ त्यही त
फेलै हुने जस्तो गरेको छ
कोही पनि त मासु भनिन्छ नि
स्टार आएको
कोही पनि मासु भन्छ क्या
क्लासिकल
त्यही त भनेको सुन्नु होइन
How do we get, when we convert something to Sturm Liouville, is there a solution for that?
Factor, integrating factor. You need to find out integrating factor and multiply by that.
Oh, you know. Yeah, it is.
Sorry.
Oh, here. Okay.
Are you prepared for the test?
We'll find out.
See you tomorrow.
Jaco,
That remains to be seen.
Oh yeah.
I think we should not record
Yeah.
Oh why? You guys don't wanna
Yeah, here.